In this section, we'll talk about amines, its different types, naming, and its basic property. All of you are familiar with ammonia, where nitrogen is bonded to 3 hydrogen and nitrogen has a pair of electrons. When you replace hydrogen of ammonia by an organic group, like in the bottom example, it's being replaced by methyl group, and it becomes methylamine. So the bonding is not shown correctly in the example because if you write down exactly the structure, it should look like this: C, H, 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 that's CH3, and then the fourth bond is with nitrogen. So in other words, there's a bonding between carbon and nitrogen, which is not explicitly shown in this structure shown at the bottom. Similarly, in 2-degree amine, the 2 hydrogens are replaced by methyl group. So here the bonding is not very nicely shown, but truly the bond is between nitrogen and carbon, and the hydrogens are like this. So make sure you understand that. Now in this case, in 3-degree, there are 3 such groups. Again, the bonding is between nitrogen and carbon, and the hydrogens are bonded to carbon. So this is 3-degree or tertiary amine. Quaternary, you'd have 4 such groups, organic groups, bonded. So basically, you'd be looking at bonding between nitrogen and carbon, and how many of those are bonded. If only one carbon is bonded, then it's 1 degree. If 2 carbons are bonded, it's 2 degree or secondary. If 3 carbons are bonded, it's 3 degree or tertiary. If 4 carbons are bonded, it's quaternary. Now let's go over a problem from page 406. This is problem number 12.1. So here you need to classify the compounds as primary, secondary, or tertiary amine. So let's go over A, 12.1a, that has CH3, CH2, and then you have CH, and then on the top you have CH3 and NH2. It's always a good idea to double check whether it has been written all right. CH3, CH2, CH, NH2, and CH3. Okay, we need to identify whether this is 1 degree or primary, 2 degree or secondary, or 3 degree or tertiary. So we need to explicitly show the bonding here in order to determine how many are bonded. So let's rewrite this. Let me change the color. CH3, CH2, and then you have CH, and then you have CH3 bonded to the same carbon, and then keep in mind this carbon must have 4 bonds, so this bond has to be with nitrogen. So nitrogen is bonded to 1 carbon, so it's 1 degree. 1 degree is same as primary amine. Let's go over part B. So there's a 5-membered ring. So there's a 5-membered ring here with nitrogen as part of the ring. When no other symbol is given, remember that others are carbon, so that's not shown. And if you want to fill in with hydrogen, keep in mind carbon must have 4 bonds. Now, Here we only care about how many carbons are bonded. So let's write down for simplicity, write down carbon in ring structure. Even though this bonding is coming from the same ring structure, but there are two such points of attachment through this carbon and through this carbon. So basically we'll be looking at how many points these carbon atoms are bonded to nitrogen. So there are two such points through which carbon atoms are bonded to nitrogen. So it will be now called 2-degree or secondary. So 2-degree or secondary amine. In part C, the benzene ring, the double bond, single bond, double bond, single bond, double bond, that's benzene ring. And then you have nitrogen, and you have 2 CH3, CH3, CH3. Of course, here the bonding is pretty clearly shown. So you can see here, let me highlight this. You can see here the nitrogen is bonded to this carbon, and this carbon. So there are 3 such carbons bonded to the nitrogen, so it becomes 3-degree or tertiary. Tertiary amine. Now in naming compounds, if I have 1-degree amine, you just write down amine at the end and write down the substitution group. Here, the group that is bonded to nitrogen is cyclopentyl group, which we get by removing 1 hydrogen from cyclopentane. So it's called cyclopentyl. So this is called cyclopentyl amine. So this part, left-hand side part, is cyclopentyl. Similarly, in the second case, we'd call it methylamine. Left-hand side group is methyl and right-hand side is amine. So basically you name the substitution group and you end it with amine. Now this is a benzene ring with COOH attached to it and NH2 at the 4th position. NH2 makes it obviously amine, but this is how you name it. The part that I'm highlighting in blue is called benzoic acid. Now you have amino group at the 4th location because carboxylic gets 1. So obviously 4th location you have amino group because we're naming it as a benzoic acid, as an acid. So that's why benzoic acid group, COOH group, would get 1. So this is 4-amino benzoic acid. Next one, this group is called phenyl group, which is a benzene ring, but when it's a substituent group, it's called phenylamine. The common name is aniline. I'd like each of you to know this because it's a very common compound. Now, if you have 2-degree and 3-degree amines, you look for the longest chain, carbon chain. Like in this case, I left out hydrogen. This is the longest chain. Longest chain has 4 carbon. Remember, 1 carbon would be methane, 2 would be ethane, 3 would be propane, 4 is butane. So obviously that's a butyl group. And other 2 are methyl group. So what you need to do here, write down how many groups are bonded to nitrogen. There's 2 such methyl groups. Of course, longest chain would be treated separately and would form the end part of the naming. So N, N. N, N means in the location is nitrogen where it's bonded. N comma N or N methyl, N methyl. Rather than saying that, we say N comma N dimethyl because there are two methyl groups. Butylamine. So this is butyl group with 4 carbon. So that's the name of the compound. So 2 degree and 3 degree amines are named like this. Now here you may be questioning, are we following alphabetic ordering? Answer is yes. Only thing is here butylamine according to rule has to be at the end. If I had say methyl and ethyl in N position, like for example N-methyl and N-ethyl, then you'd write down N-ethyl first followed by N-methyl. Now about the structure. Amines have a structure similar to ammonia. So with 4 pairs of electrons, just to remind you, with 4 pairs of electrons around nitrogen, hybridization is going to be sp3, angle will be around 109.5, but that will be squeezed to a smaller angle because of this unshared electron pair on nitrogen. It's going to squeeze the angle. So experimental value is around 108 degree in case of ammonia. Now, it's well known that amines and ammonia give basic properties. So it would give you a reaction like this, where water would split as H plus and OH minus. So H plus goes with nitrogen and giving RNH3 plus, and OH gets separated as OH minus. And that gives basic property. Now, if you want to write down equilibrium expression, we call equilibrium constant or base equilibrium constant, Kb, product concentration on the top, RNH3 plus times OH minus divided by RNH2. Then from here you can get pKb, which is minus log of Kb, or log of inverse of Kb. A stronger base, if I have a stronger base, I have a larger concentration of OH minus, then I would have a larger value of Kb. Then I would have a smaller value of inverse of Kb, which is pKb. So what that means is, if I have a stronger base, I would have a larger Kb, and I would have a smaller pKb. This is similar to a strength of acid that we discussed before in terms of pKa. A smaller pKa value means a stronger acid. Next, we are going to discuss why aniline is a weaker base compared to other amine, like say, let me write down one amine, CH3, CH2, NH2. So if I compare these two amines, this is aniline as a common name, and this is ethylamine. This is a stronger base. So in comparison with aniline, ethylamine is a stronger base. Now the question is why? Can you explain it? Yes, we can explain it on the basis of resonance structures, which shows how electron pair is distributed within the ring structure. So let me show you that, how to begin this. First, you can write down these two structures. Now they look very similar except the location of the carbon-carbon double bond. Here you have a double bond, but next time the double bond in a separate location. You can see that in a separate location. So these two structures, if I call them 1 and 2, they're different only in the location of carbon-carbon double bond. The other ones, how do I get the other ones? Let me show you one of those structures so you know how we arrive at the other 3 structures. This electron pair, again, this is the concept of resonance. When there is a pathway to distribute electron or charge is going to happen. In this case, yes, there is a pathway. If I bring this electron pair from nitrogen to in between nitrogen and carbon, this is the carbon at the center, at that point, then the carbon would have too many bonds. It would have 5 bonds, then it has to get rid of this electron pair and dump onto this carbon, next carbon, so that carbon gets minus on the ring. And that's how you get into this structure, where the minus would be on that end. Now, we can keep on writing down a structure like this. I think it would be less confusing if I redraw these structures, so that I think this structure we tried to show too many things, for which that structure could be a little confusing. So let me redraw the structure. Now nitrogen would have double bond because I moved that electron pair, NH2, and this would be plus now. And now the electron, this would get minus. Because of the electron pair, it would get minus. And of course the other bonds were intact. So this is what you're going to get. And in next step, I think from next step will be more clear to you. This electron pair, let me use a different color. Now that comes over here, and then this carbon would have too many bonds. So it would have to get rid of its electron pair onto the bottom carbon, and that gives you this structure. So I hope you are following it. In next step, electron pair here, let me use a different color, can move to the next location between carbon and carbon. Again, this carbon, don't forget that this carbon already has a hydrogen, which we didn't write down before. But for understanding purposes, let's write down this hydrogen so that you know why it's exceeding 4 bonds. So whenever the electron pair comes between this bond between 2 carbons, that's shown with blue arrowhead, that would have too many bonds, so it has to get rid of its pi electron onto the next carbon. So that's how it goes. And that's how you get this structure. So if you look at these structures now, what you see is negative charge is not localized to any particular carbon. Rather, it's distributed within the ring structure. And that gives the stability of this structure. In addition to that, 1 and 2 also suggest that electron pair, even though there is no charge developed in 1 and 2, electron pairs can have different locations. So combination of all these would give particular stability to these structures. Now, what is the result of all these combinations? The electron pair, what would have been available completely on nitrogen, is no longer available completely on nitrogen because it gets distributed throughout the ring structure. And keep in mind, the basic property depends upon how available this pair of electron is. Is it available to show its basic property or strong basic property? No, because of the distribution of electron pair throughout the ring, it's not that much available as it is in ethylamine. Ethylamine, this electron pair has no place to go. So it's going to remain localized on nitrogen, and that's why it shows a greater basic property. Now, if you're wondering that how come we can't move that electron pair, let's try that. If I'm going to move this electron pair from that nitrogen to in between carbon and nitrogen, then this carbon would have 5 bonds. It has to get rid of one of its bonds. But see, there is no weak bond here. In other case, there was a weaker pi bond which broke up. But in this case, there is no such weak bond. So in other words, this kind of transfer is not going to happen because there is no such easy passage for the electrons to go. Now here we can summarize what we just discussed. In case of amine like this, the electron pair on nitrogen is not readily available to donate, and that's why it's a weaker base than amine like this, methylamine, where electron pair is solely on the nitrogen and is readily available to donate its electron pair. Now let's look at one reaction that would show you the basic property of the nitrogen. HBr, when it reacts with this amine on the left hand side, you can think about HBr as H plus and Br minus. So electron pair goes to hydrogen because hydrogen is positively charged, so it's attracted to hydrogen, and Br minus gets separated, and this ends up with this bonding, and that would have positive charge, and since it's a positive charge, most likely it would be soluble in water. Now we have explained why methylamine or ethylamine is a stronger base than aniline, or a structure similar to that where there's a possibility of resonance. Now let's go over a problem from the book, page 411. In this problem, you're supposed to find out which pair is more basic. So let me write down number 6A, first question followed by the answer. Ethylamine, so let me write down as CH3, CH2, NH2. And don't forget that there is a pair of electron on nitrogen. Or CH3, CH2, C double bond O, NH2. Again, there is a pair of electron. Remember, nitrogen would have 3 bonds and a pair of electron. Again, first think about, is there any kind of resonance possible? What resonance would do? It would remove the electron concentration from nitrogen. In first structure, there's no resonance structure possible because these electron pair cannot go anywhere. There's no easy passage for this electron to go to another carbon. On the other hand, in the second structure, the pair of electron, I can show you that, indeed can go to this location because this carbon has a weaker pi bond, and that is going to break and leave its electron pair onto oxygen. So how this would look like, let me show you that, how it's going to look like. So this is going to look like this: CH3, CH2, CO minus double bond NH2 plus. So now you can see here, electron pair is no longer in this resonance structure. So this is the resonance, what you're looking at. Because of the resonance, electron pair has moved from nitrogen to oxygen. In other words, the net effect of this is the pair of electron on nitrogen is not that readily available compared to ethylamine. So this is a stronger base. I'm going to write down SB for stronger base. This is weaker base. Now let me go over part B. Sodium hydroxide. Let's draw a line here. Sodium hydroxide, R, C6H5NH2. It's a good idea to write down the structure. C6H5 is nothing but benzene ring. Double bond, single bond, double bond, single bond, double bond. Now you have NH2. Sodium hydroxide, we know that it splits into sodium plus and OH minus. And that's very highly ionic compound that gives 100% dissociation of OH minus in aqueous solution. Because of that high percent of OH minus, NaOH would be very strong base. So very strong base. On the other hand, aniline, again, we know that there's a resonance possible. I can make a double bond here, then this pair of electrons would move on to this. So this is how you can write down a number of structures. This electron pair on nitrogen would not be highly available. So in other words, this would not show much basic properties. On the other hand, in OH, I need to show you why from a different angle I can give the same answer. All these three pairs are very much available. So in comparison with most of the bases, sodium hydroxide is very basic. Let me go over problem number 12.6c. Again, in this case also you need to identify which of the base is more, which one is more basic between the two structures that they have given. So let me write down the question first. CH3NH. So let's write down a little bit more clearly. NH, CH3 on this end, and then another CH3 group on the other end, and you have a pair of electron on nitrogen, and you need to compare that with, again, NH. You have CH3 on one end, CH3, and on the other end you have a benzene ring. C6H5 means a benzene ring. So let me write down pair of electron on nitrogen, benzene ring, double bond, single bond, double bond, single bond, double bond. That's benzene ring. Just like before, is electron pair on nitrogen totally available? In first structure, yes, it is available because this electron pair cannot go anywhere else. It's totally localized on nitrogen and is readily available. On the other hand, in second structure, this pair of electron can go to the right because this pi electron can put its electron back to a carbon, and there will be a double bond in between nitrogen and carbon. Let me show you one such structure so that you know how this works. CH3 and H. Now you have a double bond here. This is plus. And then you have a benzene ring. So you have a double bond here, and electron pair goes in here, that's minus. And I can write more structures within the benzene ring. If I just show you the movement of arrow, like this can come over here, and then, I'm sorry, it can come the other way, because always electron would move where there's a need for it. Here you can move this electron pair, then this is going to move over here. So in other words, you can get electron pair moving to different locations on the benzene ring, just like what I have shown you before. Because of this dispersion of electron pair throughout the ring structure, this pair of electron on nitrogen is not readily available. So this is a stronger base and this is a weaker base. Because of the resonance, electron pair is not available. In part D, you don't have nitrogen, rather you have oxygen here, oxygen with CH3 on one side and another CH3 on the other side. And remember that oxygen gives 2 bonds and 2 pairs of electrons, so that it would account for 8 electrons around oxygen. So you need to compare that with the second compound, which has nitrogen and CH3, CH3, CH3. So there will be 3 such CH3, CH3, and a pair of electrons. So the question is, in which case electron pair is more available? In case of left-hand side compound or right-hand side compound? In left-hand side compound, electron pair is on oxygen. In right-hand side compound, it's on nitrogen. Here you need to look at other factor because resonance is not possible in either of these two structures. However, we know oxygen is more electronegative. So oxygen more electronegative, and nitrogen is less electronegative because oxygen is on the right hand side of nitrogen in a periodic table, and more right hand side elements, like as you go towards right, usually electronegativity is increased. Increased electronegativity means those elements are strong in pulling electrons toward itself. That means oxygen would like to keep its electron close to it rather than trying to donate it to some other element. And that's why, since oxygen show less interest in donating its electron pair, this is going to be, nitrogen compound is going to be the stronger base, and oxygen compound is going to be the weaker base. So make sure you understand this.